All right, in this section we're going to cover some material on matrices. You may have some familiarity with matrices. We're going to cover some material that might be review for you, might be some new stuff. If you've never worked with matrices before, this will get you up to speed on what we need to know. A matrix is just an array of numbers. So numbers arranged in rows and columns. And we can add and subtract matrices, but we can only add and subtract matrices that are the same size. So here's kind of what that looks like if our two matrices have 2 rows and 2 columns each. So we just add the corresponding element. So I add the first row, first column element to get that first row, first column element of the sum. I add the second row, the first row, second column element to get that sum, and so on. So we can do some examples. Let's say I want to add these matrices. They're both 2 by 3 matrices, right? 2 rows by 3 columns. So when we add these elements together, we're going to get a 2 by 3 matrix. Let's see, 2 plus 3, that's 5. I'm going to go just across the top row first. -3 plus 1 is -2. 0 plus 2 is 2. 1, now the second row, 1 plus a -3 is -2. 2 plus 2 is 4. 5 plus 5 is 10. And that is the sum of those two matrices. If I wanted to add these two matrices, we run into a roadblock pretty quickly. We can't add them. Right? Their sum is not defined. They have to be exactly the same size, meaning the same orientation. The first matrix is a 2 by 3. The second matrix is a 3 by 2. They're not the same orientation, so we can't add them together. This last one here, we're going to subtract some matrices. This works the same way that adding them does. We're just going to subtract component-wise or element-wise. So across the top row, 3 minus a -2 is 3 plus 2 or 5. -2 minus 2 is -4. Now along the bottom row, 5 minus 3 is 2, and 0 minus 4 is -4. So that's how you add and subtract. We're going to talk about multiplication next, and the first thing we're going to do is just talk about multiplying a matrix by a scalar. And a scalar is just a term that means a real number, like just a constant, a single constant. So if I'm multiplying a whole matrix just by a single number, we can do that. We just zap each element in the matrix by that factor. So I'm going to multiply every element in this matrix by -2. So we get -6, +2, 0, +4, -2, -6, 0, 2, +4. And there's that matrix. Now, if we're going to multiply two matrices together, this gets a little bit more complicated, but is actually crucial to what we're going to be using matrices for. You remember when we had to add or subtract matrices, they had to be the same size. And if we're multiplying matrices, they don't have to be the same size. In fact, even if they are both the same size, you still can't always multiply them. They have to be compatible sizes. And by compatible, we mean that the number of columns in the first matrix has to be the same as the number of rows in the second matrix. So let's say I have matrix A, and I want to multiply it by matrix B. All right, so maybe matrix A has dimensions A by B, right? So it's got A rows and B columns, and matrix B has dimensions C by D, so it has C rows and D columns. If we're multiplying them together, these two must be equal. And if those are equal, if the number of rows in the A matrix is equal to the number of columns in the if the number of columns in the A matrix is equal to the number of rows in the B matrix, then the product exists, and the product will have the dimensions A by D. So before we do any multiplying, we're just going to get some practice determining if a product exists. So here we have matrix A, which is, what, 2 by 3. And matrix B is 3 by 3. 3 rows, 3 columns. So we want to just know which product exists. AB, does AB exist? Does BA exist? So A times B. Let's write out these dimensions, 2 by 3. This is 3 by 3. So look, these dimensions match up. The number of columns in A is equal to the number of rows in B. Those are equal. So yes, the product exists. And it has dimensions 2 by 3. If we think about multiplying in the other direction, note that B is 3 by 3 still. Of course, A is 2 by 3. But now if I try to multiply them in this direction, now they're no longer compatible. So this product does not exist. So one thing we might observe here is that not only is, like the order in which we want to multiply them seems to matter, right? At least insofar as whether or not the product is defined. So we could multiply A times B, but we can't multiply B times A in this case. So now let's think about how we actually do the multiplication, and we're going to build up to it. Because what we do when we multiply two matrices together is we just repeat the process where we multiply a single row in one matrix by a single column in another matrix. So, and the row has to be of the same length as the column. So here I have a row with 3 entries and a column with 3 entries. And how we do it is we multiply the corresponding elements together. So I multiply the 2 first elements, so that's 1 times 5. I then move over and move down. So I multiply the next 2 elements, negative 3 times 2. And then move over and move down, multiply the next 2 elements, 2 times 0. And what we do is we just add these products up. So this gives us 5 minus 6 plus 0, or negative 1. Note that when we multiply a single row by a single column, the result that we get is just a number or a scalar. It's not a whole matrix, or you could think of it, I guess, as being a 1 by 1 matrix, but it's really just a single number. So when we multiply 2 matrices together, we're just going to repeat this process. We go through this process to find each entry of the new matrix. Okay, now we're going to multiply 2 matrices together. So the first thing you got to do is just determine that you can multiply. Like if you can multiply the 2 matrices together, if their dimensions are of compatible sizes and you can multiply them, then figure out what size your matrix product is going to be. So we know like what orientation it is, how many rows, how many columns, how many spaces we're going to have to fill in that matrix. And then we go through that process that we just talked about. Multiply a row by a column, find an entry. Multiply a row by a column, find another entry. So in example 536, our first matrix is 3 by 2. Our next matrix here is 2 by 4. These are equal, so we can multiply, and we're going to get a 3 by 4 product. So what I'm going to do first, I'm just setting myself up to do a bunch of work. So when I write the final answer, I probably won't need quite this much space, but I'm trying to give myself enough space to work in. I need 3 rows and 4 columns. I'm just writing dotted lines to give myself kind of space to work and define the cells that we're working with. Okay, now suppose I'm just going to start and say I want the entry in that first row, first column of this product matrix. And so to get that, I'm going to multiply the first row in the matrix on the left by the first column in the matrix on the right. So we're going to go through that row by column process. So that will be 2 times 1 plus 1 times 2. Moving over to the next entry, that's first row, second column. So I'm going to do what we did before, only with the first row multiplied by the second column. So this is 2 times negative 1 plus 1 times 1. Now, in the next entry, I'm going to multiply the first row by the third column. So I'm just sort of knocking out the first row first. Multiply the two first elements, that's 2 times 0 plus then 1 times 2. And then last, first row, fourth column, I'm going to do 2 times 1 plus 1 times 0. There's the first row. I got every element, or at least what I need to compute, right? To get each element in the first row, I just kept looking at the first row in this matrix on the left here, and then just kind of moved down to work each column to get each entry in each column of the first row. If we want to, and we do, if what we want is to get the entries in the second row, I'm going to just repeat this whole process, only I'm going to do it using the second row of that first matrix. So second row, first column, second row by first column. And that's going to give us 1 times 1 plus 0 times 2. Moving on to the second column here, 1 times negative 1 plus 0 times 1. And then the third column will be 1 times 0 plus 0 times 2. Now as you work these out, you might just decide, you know what, I can find these products in my head pretty easily and then just add them up, and that's fine. I'm kind of just showing you the long, each step of the process to make sure that we see how we actually do the multiplication. And now the last column, 1 times 1 plus 0 times 0. We'll do this one more time with the third column, or third row, sorry, of the first matrix. Starting with the first column, we're going to have negative 1 times 1 plus 2 times 2. In the next column, negative 1 times negative 1 plus 2 times 1. And then next column over, negative 1 times 0 plus 2 times 2. And negative 1 times 1 plus 2 times 0. So there's sort of all the nitty-gritty of how we find each entry. Now I'm just going to do the arithmetic. Let's see, that's 2 plus 2 is 4. Next entry over in the top row, negative 2 plus 1 is negative 1. 0 plus 2 is 2. And in the last entry in the first row, 2 plus 0 is 2. Second row, 1 plus 0 is 1. Negative 1 plus 0 is negative 1. 0 plus 0 is 0. 1 plus 0 is 1. Last row, negative 1 plus 4 is 3. 1 plus 2 is 3. 0 plus 4 is 4. Negative 1 plus 0 is negative 1. And there is the product. Okay. Let's do another one. Here we have a couple of matrices. We want to find both products if they exist, AB and BA. So let's think about AB first. Matrix A is a 2 by 3. Matrix B is a 3 by 2. So we'll see that these they are compatible sizes, and the product is a 2 by 2. So now I'm just going to write out the matrices next to each other in the appropriate order. So here's matrix A, matrix B, and we're going to get a 2 by 2. So now let's see, the first row by the first column. Now this time what I'm going to do is just find the products and then write their sum. So 2 times 1 is 2, plus 3 times 2 is 6, plus -1 times -1 is 1. Moving over to the second column, 2 times 3 is 6, plus 3 times 0 is 0, plus -1 times 2 is -2. Now let's do the same thing, but using the second row. -2 times 1 is -2. 1 times 2, moving over and down, 1 times 2 is 2. 2 times -1 is -2. And second row, keeping with the second row, times second column, that's -2 times 3 is -6, plus 1 times 0 is 0, plus 2 times 2 is 4. And we find that AB is equal to, let's see, that's 9, and then across the row, top row, 9, 4. On the bottom row, -2, -2. So there's AB. Let's try BA. So B is a 3 by 2, A is a 2 by 3. Again, they're still defined, right? Those are these dimensions are compatible. We're going to end up with a 3 by 3 this time. So I'm going to start by writing out the matrices in the appropriate order. So matrix B is 1, 2, -1, 3, 0, 2 for the second column. And then matrix A, first column 2, -2, then 3, 1, -1, 2. I'm going to make room for a 3 by 3 matrix. Okay, so I'm going to start with the first row on the first matrix on the left, and then first column, and that'll get me the first row, first column entry. So we have 1 times 2 is 2, plus 3 times -2 is -6. Moving over to the second column, 1 times 3 is 3, plus 3 times 1 is 3. Now to the last column, 1 times -1 is -1, plus 3 times 2 is 6. Let's do this again. Now starting with second column. Second column first, starting with the second row of the first matrix. So second row by first column, 2 times 2 is 4, plus 0 times -2 is 0. Second column here, 2 times 3 is 6, plus 0 times 1 is 0. And then last column, 2 times -1 is -2, plus 0 times 2 is 0. And then now let's work on the last row, starting with the last row of the first column, and then beginning with, the last row of the first matrix, and beginning with the first column of the second matrix. So -1 times 2 is -2, plus 2 times -2 is -4. Last row by second column, so -1 times 3 is -3, plus 2 times 1 is 2. And then last, -1 times -1 is 1, plus 2 times 2 is 4. Now this gives us, we just find the sums. See, across the top row, -4, 6, and 5. Then second row, 4, 6, -2. Last row, -6, -1, 5. This is B times A. So, you know, one thing we might observe, this was an instance where we actually could multiply both matrices. We could find both products in either direction. And when we did, we got different results, right? So AB, the matrix AB, is not equal to the matrix BA. And so one takeaway here is that matrix multiplication is not commutative. Okay, so we've talked about division. Now what we're going to do is think about how we find the inverse of a matrix. You know, not all products are defined. We don't really have a division of matrices, but we do sometimes have inverses, just like when we were working with Zn, or Z mod NZ. And when we were working with the modular arithmetic, right? You know, for example, in Z5, we learned that the inverse of 2 is equal to 3 mod 5. And that's because 2 times 3 is equal to 6, and that is equal to 1 mod 5 in Z5. So if we're talking about inverses, we're still talking about what do we multiply by this matrix to get 1? And that begs the question, what is our 1 in the world of matrices? What is that multiplicative identity? So let's find the product given here in 5.38. We imagine we're starting with a matrix on the left that just has arbitrary entries, so A, B, C, D, and then we're multiplying that by this matrix, 1, 0, 0, 1. The product is defined because they're both 2 by 2 matrices. The product is defined and we'll get a 2 by 2. So if we do top row, first column, we get A times 1 plus B times 0. And then if we do the next column, A times 0, which is 0, plus B times 1, which is B. Now let's focus on the second row. C times 1, C plus D times 0 is 0. And now second row, second column, C times 0 is 0, plus D times 1 is D. And simplifying, we get A, B, C, D. It's the same matrix, right, that we started with. So here we took this matrix, A, B, C, D, we multiplied it by this other guy here, and we got the same matrix right back. That means that this matrix, 1, 0, 0, 1, is like our 1. It's we call it an identity matrix, like a multiplicative identity, and this is the 2 by 2 identity matrix, 1, 0, 0, 1. Because we have to have different sizes of matrices to be able to multiply them together, right? The matrices have to be of compatible sizes. We have an identity matrix of each size. So this was the 2 by 2 identity matrix. The identity matrix is always square, right? Same number of rows as columns. And the n by n identity matrix is just the square matrix that has ones down the what we call the principal diagonal, that is the top left to bottom right, and then zeros everywhere else. So we denote that matrix by I sub n, and I sub 3, the 3 by 3 identity matrix, then would just be ones down the diagonal and zeros everywhere else. There's that 3 by 3 identity matrix. So now that we know what the identity is, we can define an inverse. So not every matrix has an inverse. In order to have an inverse, it's got to be a square matrix, but still not all square matrices have inverses. If M has an inverse, we denote it with a little superscript -1, so we call that M inverse. And it will have the property that when I multiply M by M inverse, or if I multiply in the other direction, I'm going to get the identity matrix of the appropriate size. So we could verify, right, that these two matrices are inverses of each other. And the way we'll do it is just by multiplying them. If we multiply them together and we get the identity matrix, then that means they're inverses. So let's start with the top row. I'm going to do first column. So 3 times 7 is 21, plus 4 times 5 is -20. Moving along, top row, second column, 3 times 4 is 12, plus 4 times -3 is -12. Second row, first column, -5 times 7 is -35, plus -7 times -5 is a +35. And second row, second column, -5 times 4 is -20, plus -7 times -3 is +21. And once we simplify, we see that we get 1, 0, 0, 1. That is the identity, so these are inverses of each other. Okay, so now we're going to work on how we find the inverse of a matrix ourselves. I've got a procedure kind of written out here, and I'm just going to kind of describe this procedure by going through an example. And what we're going to do is find the inverse of this matrix. So first of all, we need to make sure that the inverse of the matrix exists. And in order for that to be the case, we mostly just need to make sure that one row is not a multiple of the other. So we have 1, 3, 2, 7. If this were 1, 3, 2, 6, we'd have a problem because in the second row would just be a multiple of the top row, entry for entry. But as long as one row is not a multiple of the other, then an inverse should exist. So here's what we do. We set up what we call an augmented matrix. So here's what step 1 looks like. The augmented matrix, we start with the given matrix on the left, 1, 3, 2, 7. Now I'm going to draw a little vertical line, and then I'm going to put in this case, the 2 by 2 identity right next to it. There's my starting point. Now we're going to do a bunch of operations, what we call Gauss-Jordan elimination. We're going to do a bunch of operations, and our goal is that this matrix on the left, we're going to make it look like the 1, 0, 0, 1, make it look like the identity. And once we've done that, then what we end up with on the right side is the inverse matrix. So that's the idea. So when we go through this process, we want it to look like 1, 0, 0, 1, and we have to do so in a particular order. We have to start by getting this to what we want it to look like, and it's already there, right? We want this to look like 1, 0, 0, 1. So we want a 1 in the upper left entry, and we have it. But the way we're going to go about it is we get that 1 where we want it, then we zero out the next entry. Then we get the 1 where we want it here, and then we zero out the entry there. So we start in the top left and obtain our goals in this kind of counterclockwise direction. The operations that we're allowed to perform is that we are allowed to interchange 2 rows. So we could swap 2 rows from each other. We are allowed to multiply a row by some non-zero constant, just straight across. Multiply everything in a row by the same thing. And we're allowed to add a multiple of one row to another row. So I could say, oh, let's multiply this row by something and add it to the next row. That's the first thing we're going to do here. All right, so we've already got the 1 where we need it. If I didn't have a 1, that's where I would do probably this operation here, and I'd just multiply by the reciprocal or something. But we want a 0 right here. And the way we're going to get a 0 is by subtracting 2. We're not allowed to just subtract each number by the same thing, by the same number. Like I can't just say, oh, let's take row 2 and subtract 2. The only way I'm allowed to subtract or add a number is by doing this third operation. I have to add a multiple of one row to another. So now I'm going to use the fact that I've got a 1 sitting right above it that I'm going to use. I'm going to multiply row 1 by -2 and add it to row 2. Now I'm not actually changing row 1 in this process. I am simply multiplying row 1 by -2 temporarily so that I can add it to row 2, and I'm putting the result in row 2. So look here, row 2 is the only row changed. Row 1 is going to stay as is. Row 2. Now what goes here is -2 multiplied by whatever's in row 1, so -2 times 1, which is -2, and then I'm going to add 2. And that gives us 0. For the next entry here, -2 times whatever's in row 1 above it, so that's 3, plus whatever's in this row to begin with, which is 7. So -6 plus 7 is 1. Then in our next entry, -2 times whatever is above it, which is 1, plus whatever was in that row to begin with, or in that row to begin with, which is 0. So that gives us a -2. And then last, we have -2 times whatever's above it, 0, plus whatever was in this row, which is 1, and that'll just give us 1. So I've got this 0 where I want it, right? So look, we've got the 1 where we want it there, we've got the 0 where we want it, and it just so happens that we've got this 1 where we want it here. That doesn't always happen. Sometimes I would actually, the next thing I'd have to do is say, okay, I want to get a 1 there, but we already have the 1, so our next goal is to get a 0. And the way I'm going to get a 0 there is by subtracting 3, and the only way I can subtract 3 is to subtract a multiple of one row. So I'm going to use the second row. I've got a 1 sitting right there. I'm going to multiply the second row by -3 and add it to the first row. Now, this isn't going to change the second row, because I'm just multiplying that second row by -3 temporarily so I can add it to row 1. I am only changing row 1. That's the only row that gets changed. Also notice that because I have a 0 right here, that when I add a multiple of the second row to the first, this 1 that's sitting in this sitting right above it, that's not going to get changed. I'm going to add a multiple of 0 to that one entry. So this is why we go about it in this order, like starting in the top left and going like counterclockwise, is because as I do these processes, I'm guaranteed not to undo some of the progress I've made. So we know that row 2 is unchanged. And I'm going to write that in. And now, let's see, I'm adding -3 times row 2 and adding it to row 1. So right off, here's what I'm going to do. Here's row 2. I'm just going to highlight it. The first thing I'm going to do is multiply each of these by -3. So I'm just going to write out what I get when I multiply each number by -3. So I get 0, I get -3, I get +6, I get -3. Now I'm going to take each of these and add it to the value that's up here. So I'm going to take this number and add it to that. I'm going to take this number and add it to that. This number and add it, this number and add it. And when we do that, we get 1. And then our next entry, -3 plus 3 is 0. Then 6 plus 1 is 7. -3 plus 0 is -3. This looks like the identity. We have the identity sitting on the left. That means that this is the inverse. So we have just deduced that the inverse, so we started with that matrix, the inverse, so I'm using that superscript -1 notation, the inverse of that matrix is equal to 7, -3, -2, 1. And if you multiplied them together, you could check that you will get the identity. Alright, so we're going to do one more. We're going to find the inverse of this matrix. I'm going to start, like we did before, writing out the matrix that's given, writing out the augmented matrix. So there's the given matrix. I'm going to put the identity right next to it. Now what we want first, to begin with, we need a 1 here. And so the way I'm going to get a 1 is just by multiplying that top row by the reciprocal of 4. I'm going to multiply row 1 by 1/4. So 1/4 times row 1, putting that into row 1. Row 2 is not going to be changed in this process. So there's row 2, same as it was. And then I'm going to multiply each element in row 1 by 1/4. So 1/4 times 4 is 1. 1/4 times -1 is -1/4. 1/4 times 1 is 1/4, and 1/4 times 0 is 0. So I've got the first thing that I want, that 1 in that location. Now we want a 0 below it. And the way I'm going to get a 0 is I have to be able to add 6, right? I've got a -6 sitting there. I want to be able to add 6. So I'm going to use the fact that I got a 1 sitting right above it. I'm going to multiply row 1, that top row, by +6 and add it to row 2. So I'm going to have 6 times row 1 plus row 2 into row 2. Row 2 is the only row being changed. Row 1 does not change in this process. And let's see, so now we're going to figure out what we get in the second row. So we're multiplying the top row by 6. So I'm just going to write in the matrix above here, I'm going to write what we get when we multiply each of these entries in the top row by 6. So I get a +6. 6 times -1/4 is -3/2. 6 times 1/4 is 3/2. And 6 times 0 is, of course, 0. Now I'm going to take each of these numbers I wrote in blue, and I'm going to just add it to the entry in the second row. So 6 plus a -6 is 0. -3/2 plus 2 is a +1/2. 3/2 plus 0 is 3/2, and 0 plus 1 is 1. Okay, next, we want a 0. Or sorry, we want a 1 in that location. And I'm going to get it by just multiplying through by the reciprocal. Let's multiply row 2 by 2. put the result into row 2. Row 1 is unchanged in this process. Row 2 becomes 0. If I zap everything with a 2, 1/2 times 2 is 1, 3/2 times 2 is 3, 2 times 1 is 2. And then last, we want a 0 up here. And the way I'm going to be able to add, to get a 0 there is to add a quarter. So I'm going to take row 2, multiply row 2 by positive 1/4, add it to row 1, putting the result into row 1. Now row 1 is the only row changed. Row 2 is left unchanged, so I'm going to write that as is. And above, let's see, I'm going to write out what we get. I'm going to write out in blue what I get when I multiply each element in row 2 by a quarter. So that would be 0, 1/4, this would be 3/4, and 2/4, or 1/2. And then I'm just going to add to the entry above. So 0 plus 1 is 1, 1/4 plus negative 1/4 is 0, 3/4 plus 1/4 is 1, and 1/2 plus 0 is 1/2. So look, here we have the identity on the left. That means we're done. And this matrix that we have sitting here on the right, that's the inverse. So this means that this matrix that they gave us, 4, -1, -6, 2, the inverse of that matrix is 1, 1/2, 3, 2.